Imagine stumbling upon a cosmic car crash involving not two, but 5 entire galaxies smashing into each other when the universe was just a cosmic toddler. That's exactly what astronomers have witnessed, and it's shaking up everything we thought we knew about early galaxy formation. Using the combined power of the James Webb Space Telescope and the Hubble Space Telescope, researchers have identified what they're calling JWST's Quintet, an extraordinary collision system involving at least 5 galaxies from when our universe was barely 800 million years old. To put that in perspective, that's like catching a rare event when the universe was only about 6% of its current age. But here's where it gets controversial. This discovery might be challenging our fundamental understanding of how quickly massive structures can form in the early cosmos. Galaxy collisions aren't exactly uncommon in the universe's grand scheme, but they typically involve just 2 galaxies dancing their final gravitational waltz before merging into one. What makes this discovery absolutely mind-blowing is that we're looking at 5 galaxies, plus an additional 17 smaller galaxy fragments, all caught in the act of merging simultaneously. Discovering a system with 5 physically connected galaxies is exceptionally rare. Both in our computer simulations and in actual observations, explains Wida Hu, the lead researcher from Texas A&M University, who spearheaded this groundbreaking study. The chances of detecting even one multiple galaxy merger are quite low, which makes us wonder, did we just get incredibly lucky? Or are there more of these systems hiding out there than we ever imagined? These aren't just any ordinary galaxies either. They belong to a special category called emission-line galaxies, which act like cosmic lighthouses broadcasting brilliant signatures of hydrogen and oxygen in their starlight. These chemical fingerprints tell us something exciting. These galaxies are absolute star-making factories, churning out new suns at an incredible pace. The research, published in Nature Astronomy this past August, showcases the incredible synergy between our most advanced space telescopes. While Hubble had previously spotted some of these galaxies individually, it was JWST's near-infrared camera that revealed the smoking gun, a massive halo of gas enveloping the entire group like a cosmic embrace. And this is the part most people miss. The breakthrough came when JWST showed that all 5 galaxies share the same redshift measurement. For those unfamiliar with astronomical jargon, redshift is essentially our cosmic measuring stick. It tells us how far away and how ancient an object is by analyzing how its light has been stretched during its journey across the expanding universe. The fact that all 5 galaxies have identical redshift readings proves they're not just coincidentally lined up in our view. They're genuinely interacting and bound together in the same cosmic neighborhood. Who suggests there might be even more faint or hidden galaxies connected to this system that we haven't detected yet? Uncovering these cosmic hide-and-seek champions will require even more sophisticated multi-wavelength observations, essentially looking at the same region of space through different cosmic filters. Christopher Consellis, a professor of extragalactic astronomy at the University of Manchester, who wasn't involved in the study, puts this discovery's rarity into stark perspective. If you examine all galaxies in the universe, roughly 20 to 30% will be involved in some kind of merger. However, these will almost always be simple 2-galaxy affairs. The fraction involving multiple merging systems like this one is dramatically lower. We're talking about less than 1%, and quite possibly much rarer than that. The measurements are equally staggering. The 2 primary galaxies in this cosmic pileup are separated by approximately 43,300 light-years, while the most distant pair spans about 60,700 light-years. To give you a sense of scale, our entire Milky Way galaxy stretches roughly 100,000 light-years from edge to edge, so these galaxies are practically on top of each other in cosmic terms. The fact that these galaxies are so spatially close together strongly suggests they're destined to complete their merger, Consolis notes, though there's some room for interpretation about whether some of these objects might actually be different parts of the same galaxy rather than separate entities. The system bears a striking resemblance to a more familiar cosmic collision much closer to home, Stephan's Quintet. This local universe counterpart involves 4 galaxies locked in merger, with a 5th galaxy that just happens to appear in the same patch of sky but isn't actually participating in the cosmic dance. There's a remarkable similarity in the bridge of material connecting 2 galaxies in JWST's Quintet, a feature we also observe in Stephan's Quintet. Who explains? These bridges, called tidal tails, are the telltale signatures of gravitational interactions stretching and warping the galaxies. However, the star formation rate in JWST's Quintet is dramatically higher. But here's where it gets controversial. While Stephan's Quintet consists of much older, more mature galactic systems in our cosmic neighborhood that have largely settled down, JWST's Quintet represents galaxies that are absolutely bursting with activity. They're gas-rich powerhouses creating new stars at rates far exceeding what astronomers expected for that early epoch in cosmic history. The combined stellar mass of JWST's Quintet, including all 5 main galaxies and 17 smaller clumps, equals roughly 10 billion times our Sun's mass. The research team predicts that this high mass and explosive star formation rate indicate these merging galaxies might evolve into what astronomers call a quiescent galaxy, essentially a cosmic retiree that stops forming new stars entirely. This transformation could occur somewhere between 1 billion to 1.5 billion years after the Big Bang. And here's where things get really intriguing. Previous JWST studies have already detected several of these dead galaxies in the early universe, raising fundamental questions about how galaxies could possibly burn out so quickly when the cosmos was still in its infancy. Consolis points out that predicting the future of merging galaxies remains one of astronomy's biggest puzzle pieces. They might continue as star-forming galaxies but with reduced activity, or they could completely shut down and become passive over time. The system's ultimate fate will also depend heavily on whether these galaxies host actively feeding black holes, which could rapidly extinguish star formation like cosmic fire extinguishers. If JWST's Quintet does transform into a dead system, it could potentially solve the mystery of how massive quiescent galaxies form so rapidly in the early universe, through the merger of smaller star-bursting galaxies rather than through slower, more gradual processes. However, there are limitations to what we can currently observe. While JWST's near-infrared camera provides incredibly detailed images showing the shapes and structures of these cosmic objects, it doesn't offer the precise spectroscopic information needed to measure crucial properties like metallicity, the motion and dynamics within the system, or the exact nature of the gas contained within these galaxies and clumps. The discovery raises fascinating possibilities for future research. If astronomers can identify more systems similar to JWST's Quintet in upcoming surveys, we'll be able to study how frequently these multiple galaxy mergers occur, understand their fundamental nature, and examine the specific conditions that allow them to form. This research could ultimately determine whether these systems represent a rare but predicted class of objects that fit within our current standard model of the universe, or whether they're pointing toward entirely new cosmic mechanisms we hadn't yet understood. And this brings us to the most thought-provoking question of all. Are we witnessing rare cosmic accidents, or are these multiple galaxy mergers actually more common than we've assumed, hidden throughout the early universe and waiting to be discovered by our increasingly powerful telescopes? What do you think? Could this discovery be hinting that our models of early universe evolution need a major revision? Are we perhaps underestimating how quickly and dramatically cosmic structures could assemble in the universe's youth? The implications could reshape our understanding of cosmic evolution itself. And I'd love to hear whether you think we're on the verge of rewriting the textbooks. or simply filling in missing pieces of an already solid puzzle.